Howdy, howdy. This is Mr. Potter. Throughout Chapter 3, we stress the importance of finding a tangent line to a curve. And of course, the big question that's often asked is, why is finding the tangent line so important? And so I want to talk today about why finding a tangent line is so important. And this process is called the linearization of functions. So what I want to do is I want to talk about a particular function. Let's say y equals the square root of x. So if I take a look at this function near the point 64, comma 8, if I go ahead and take a look at this around that point, if I go ahead and graph this, let's graph y equals the square root of x. And I want to adjust the window so that I'm looking around 64, 8. So let's go ahead and do 63 for my minimum max and 65 for my maximum max. And because the square root of 64 is 8, I'm going to set my y window from 7 to 9. So I've got this very focused area on this square root curve right around 64, 8. And when I take a look at the graph, I notice that this graph looks almost like a line. And so if we actually go through the process and find the tangent line, of course, the idea if I want to find the tangent line is I have to find the derivative. So the derivative of x to the 1/2 would be 1/2 x to the negative 1/2, or 1 over 2 radical x. And that means the slope of my tangent line is going to be 1 over 2 times the square root of 64, which is 1/16. And so my tangent line is going to be y minus my y coordinate equals 1/16 times x minus my x coordinate. So if I take a look at this function, y equals 8 plus 1/16 x minus 64, and I compare the graph of this line to the graph of this function that we just did. Let's do that. So I'm going to go back. I'm going to type in my y equals. And down here, I'm going to do 8 plus 1/16 times x minus 64. And when I graph this function, there's no difference. In other words, these functions essentially coincide. If I had f3 to trace, I notice at 64, both of these are going to be 8. But even if I go out here a while to like 64.3, the square root graph gives me 8.018, but if I move to the linear graph, I get 8.0189. So there's not much of a difference between these two graphs. So the reason that we do these tangent lines is because the tangent lines provide a very accurate approximation. Near the point of tangency. So these provide a very good way to look at these problems near the point of tangency. So if I wanted to approximate the square root of 66, and according to my calculator, when I type that on, I get 8.1240308. If I try and put 66 into this tangent line, I get y equals 8 plus 1/16 of 66 minus 64. So I get 8 and 1/8 out of this, which would really be 8.125. And notice that even though I'm 2 units away on the x-axis, I'm very close. I'm almost within 3 decimal places of accuracy, or within 0.01, within 0.1% of the correct answer here. And so tangent lines provide a very accurate approximation. As long as we're near the point of tangency, I'm going to run into more difficulty if I try and get farther away from the point of tangency. Let's say, for example, if I wanted to approximate the square root of 49. Now I know that this is 7, but looking at it from the tangent line, I'm going to get 8 plus 1/16 of 49 minus 64. So I end up with 8 minus 15/16. So I end up with 7.0625. Notice that I'm off by about 1% here. So tangent lines do provide a way to approximate functions. They're very, very accurate as long as I'm near the point of tangency. They're not so accurate the farther away I get from the point of tangency. tangency. Of course, in this situation, I would have chosen a different point of tangency. I would have chosen near the point 749 to approximate values of the square root near 49. So we're going to go through several examples of this to kind of show the process behind it. So I'm going to start off with this example here. I want to approximate the cubed root of 997. Now I'm choosing these values for a very specific reason, because there are nice points near these x values. So I'm looking for a nice perfect cube near 997. And I happen to know that 10 cubed is 1,000. So I know that the point 1,000, 10 would be a point on the cubed root graph. That would be very near to this. And so if I could use the tangent line at this point, at this 1,000, 10, then I could get a very good approximation using the linearization. So if y is x to the 1/3, my derivative would be 1/3 x to the negative 2/3, or 1/3 of the cubed root of x squared in the denominator. So the cubed root of 1,000 is 10, 10 squared is 100. My slope ends up being 1/300. So when I'm looking at my tangent line, I'm looking at y minus my y coordinate equals my slope, 1/300th, times x minus my x coordinate. And now I'm ready to evaluate for my particular value. I want to approximate the cubed root of 997. Now, according to my calculator, this is 9.9899898983. And of course, that's going to continue on because it's irrational. But if I take a look at it through the approximation, where I've got y equals 10 plus 1/300th of 997 minus 1,000, I see that I get negative 3 here. And 3/300ths is really 1/100th. So I really have 10 minus 1/100th, or 10 minus 0.01, or 9.99. And notice that this value that we get is very close to this value. As a matter of fact, if I round from this millionth position to the thousandth, to the 100th position, I actually get that. So it's a very close approximation. That's why linearization is such a good approximation, because those graphs are so close to each other. And that's why finding the tangent line, or being able to find a tangent line at a particular point, is such an essential skill. So I want to do this with some more complicated functions. Let's take a look at y equals the natural log of 1.02. And again, remember that I need to find a good point near 1.02. And I happen to know that the natural log of 1 equals 0. So I know that I can take a look at the natural log of x function near the point 1, 0. So if this is y, my derivative would be 1 over x. And my slope is going to be 1 over x at my good point, which is where x equals 1. So my slope is 1. And so my tangent line becomes y minus 0 equals 1 times x minus 1. So if I've actually type in the natural log of 1.02 in my calculator, I get 0.0198 0.26673. And of course, that's going to continue because it is an irrational number. But if I use my linearization here, if I substitute 1.02 for x, I end up with y equals 0 plus 1 times 1.02 minus 1, or I get 0.02. And I get a value that's very, very close to the actual value. Now, later on in chapter 9, we can talk about how far off this approximation is. For now, though, it's important to know that the tangent line gives us a very, very good approximation. As long as we're near this point of tangency, that's very, very important. So I could just as easily take a look at y equals e to the x at x equals 0.98. 0.098, I mean 0.098. I want to be very close to a nice point. So near 0.098. And of course, I'm looking at graph near the point 0, 1, because I know that that is a nice value for an exponential. I know the exponential's exact value at that point. But if this is y, to find the slope, I need to find the derivative at that point. So the derivative of e to the x is e to the x, and so my slope ends up being e to the 0, which is 1. And so my equation of the tangent line is y minus my y coordinate equals my slope times x minus my x coordinate. And when I substitute in this 0.098, I'm going to get y equals 1 plus 1 times 0.098 minus 0, or 1.098. This is my approximation. If I look at the exact value here, I find out that if I'm dealing with e to the 0.098, this is approximately equal to 1.102 ... So again, I'm looking at these, and these are fairly good approximations. I'm finding these approximations are well within 1% error. They're not perfect. They're not supposed to be perfect. These are linearizations. These are approximations using the tangent line. So I want to do one last example. I want to take a look at 2.003 raised to the 6th power. Now, I know that this is very, very close to an integer being raised. So I want to look at x to the 6th when x equals 2. And 2 to the 6th is 64. And if I'm looking at this as my function, y equals x to the 6th, my derivative would be 6 times x to the 5th, and my slope would be 6 times 2 to the 5th, and 6 times 32 is 192. So my tangent line becomes y minus 64 equals 192 times x minus 2. And so if I look at this from this particular value, I'm going to be looking at my linearization being 64 plus 192 times 2.003 minus 2, or 64 plus 192 times 0.003. And this comes out to be 64.576. Whereas if I actually type in 2.003 to the 6th in my calculator, to get 64.578. 1643249 dot dot dot. So these are very good approximations, and I can do this with logarithms, exponentials, polynomial terms. I can do this with trigonometric terms, anything that I can find the derivative, and most importantly, find a nice point near the point that I'm trying to estimate. The main reason that linearization works is because I want to be able to find the point, and I want to be able to find the derivative easily. And so if I can find a nice point that's near where I'm trying to estimate, that's going to make these very smooth to work with. So when asking the question, why is it so important to be able to find the tangent line at a particular point? This is why. Finding these approximations using linearization, using tangent lines to find the approximate y value, is an essential skill. It's something you can do just very quickly, even quicker than just grabbing a calculator and finding these values sometimes. Or you could be out in the field and not have access to a calculator. But this is something you could just scroll out on pen and paper. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.